Welcome to the lab on spanning tree. Now, a lot of times we have to connect multiple switches together in order to increase the size of our network to provide redundancy for a lot of reasons. Now, the problem with connecting switches is that you can actually create loops in your network where a packet trying to reach its destination can just go around and around and around forever and never actually reach that destination. Spanning tree is a protocol that evaluates your network, determines what ports are connected to switches, finds these loops automatically, and will disable ports that might cause loops but still allow your network to function correctly. Now this concept is difficult to understand just talking about it. That's why we're going to actually implement spanning tree and see how this protocol works behind the scenes. We are also going to look at a faster version of the spanning tree protocol called Rapid PVST+. That's Cisco's proprietary version of the spanning tree protocol. So we need some hardware. I'm going to add that when I look at the network diagram. So we should start with a clean switch configuration, nothing fancy to it. So let's cable this network. So I'm going to click on switches, add 1, 2, 3. I'm going to change the labels to match the diagram. S1, S2, click the wrong spot, that's why this popped up, it's fine. And S3, so these switches are booting in the background, that's great. I need 3 computers, so I'm going to click N devices and click on this generic PC. Let's stick this close to where it is on the diagram so that it matches. So this is, I'll label these as well. Let's computer A. Computer B, and computer C. Now I am going to skip these serial cables for the console port now because I'm in Packet Tracer. I can click on each of these switches and perform the configuration without having to connect that cable, so I'm just going to skip that part. If we are connecting physically, of course, you have to make the initial configurations using that console cable port. But we're using the magic of Packet Tracer, so we're not going to do that. Now, you can see in this diagram that I've got a red cable connecting the switches. This red is just in my diagram notation, it just means a crossover cable. So remember, a crossover cable is an Ethernet cable that just connects 2 devices of the same type. So switch is the same type as a switch, so we're going to use a crossover cable. In Packet Tracer, we can find that, click on our connections icon. This straight line, not dashed, is a copper, meaning Ethernet straight through cable. The dashed one is a Ethernet copper crossover cable. So this is the one we want in Packet Tracer. So let's see, for 1 to 2, I'm going F01 to F01. So F01, click on switch 2, F01. Those will be amber lights. It's important to note the color of these interfaces in this lab especially. So we're going to go S2, F03 to F01. And then to connect S1 to S3, we're going to go F03 to F03. The remaining connections, we are going to use a straight through cable. So we're going to connect computer A. There's only one choice, fast Ethernet 0. I'm going to connect it to F06. I'm going to connect computer B to F012. I'm going to connect computer C to F018. And now those choices, 6, 12, or 18, they're basically random. I could essentially plug this into any unused Ethernet port. But we're just going to follow the lab guide. We're going to do everything correctly. Okay, so let's see what we need to do. We need to set the host name for all 3 switches. We can do that. So we're going to enable, configure terminal, and change the host name to S1. So what should change as soon as I hit enter? Think about it. Okay, the host name changes, and we can see that reflected in the prompt here. So that is good. We can open up S2. We'll just kind of do them side by side right now. Got some status messages there. Well, that's fine. Oops, I'm on the config tab. Can't do anything on the config tab here. That's why hitting enter doesn't do anything. If I come to this CLI tab, now I can enable configure terminal, say host name S2. That's good. And click S3. Now drag this over. I'm on the CLI tab, so I'm going to hit enter to refresh that prompt. Enable config T, hostname S3. Okay, hostname is all set. Good. Now I'm just going to run these same commands on all the machines. So line con 0, that's our console. I'm going to change logging synchronous. So remember what that command does. Just to make it so Cisco won't interrupt our typing. We're going to password protect it with password class. Okay, so through the magic of digital editing, you can see that I added a command here, the login. If I don't put that login there, the password actually isn't really active. So now I'm going to exit, enable secret Cisco, and add the banner. No, see if I can type unauthorized correctly for the first time. Unauthorized access, I think I got it. Here we go. Now I need to do that same thing on S2 and S3. So line con 0, logging synchronous, password class, login, exit, enable secret Cisco, and banner MOTD, message of the day, no unauthorized access. Over to switch 3. 0. Logging synchronous. The logging synchronous is going to be extra important today because the switches are going to talk a lot between each other. Login, exit, enable, secret, Cisco, banner message of the day, no unauthorized access. Okay, so I spelled unauthorized correctly 3 times. That was amazing. I just noticed that I misspelled the word access 3 times. That's okay. Hopefully this would hold up in a court of law and a criminal isn't going to claim that he or she did not know what access, A-C-E-S-S, meant. Could fix that. If you just run the command again, it'll overwrite what you did last time. Using the up key, I get the last command that I typed. So this will work on your physical switch as well. It's not just a packet tracer feature. There, now we are fully protected. People know they can't mess with us. Now we're going to do something interesting. We are going to shut down all ports administratively. Let's look at S1 first. Now I'm in config mode right now, but if I want to use the show IP int brief command, I have to run do show IP int brief here. And let's look at the status. So right now the status of all these interfaces, they're basically up or down. They're up if something is plugged in, they're down if something is not plugged in. That's fine, that's the way it should be right now. But in config mode, I'm going to turn all them off. So I'm going to say int interface range. We use the range keyword to indicate that we are going to configure more than one interface at a time. So F0/1-24. Don't put any spaces in there. In this F0/1-24 won't work. Now you see the prompt will change to config if for interface range. So it means I'm working on more than one interface. Now let's look at my lights. I'm going to say shut down. All of a sudden, every light, every blinky light, every connection connected to S1 just went red. So that's supposed to happen. That's good so far. But now we need to enable interface 6, the one computer A is connected to. So let's do that. I'm going to exit and say int. I'm not going to put the range command because I'm only going to configure one interface, F0/6. I'm going to run the command switchport mode access. Now what this command does, type that typo again. Hopefully I figure out how to type the word access today. Switch port mode access. An access port is a port on a switch that's intended to be used by a computer or a printer or a server or some sort of device that would be used by a user. It's kind of the purpose of our network, all of these access. The other types of ports might be a trunk port, which could be used to connect two switches. But an access port is good for all of our devices, computers A, computer B, and computer C right now. I'm going to say no shut. This is the opposite of the shutdown. I could say no shut or no shutdown. It does the same thing. So when I hit enter there, you can see the lights will change. Computer A has already got blinky lights on its end, but the light is amber on switch 1's end. So it's trying to establish that connection. So that's good. If I run do show IP int brief here, you can see that almost all of these interfaces now are administratively down. The only difference is interface F06, which is up. So I turned everything off except for that one. Turned it back down. Sorry, I turned off F01 through 24. I didn't touch these gigabit Ethernet ports. But I think you could have figured that out. Okay, that's good. So I need to shut down that range of ports on all the switches. So int range of 0, 1 through 24. Shut, exit. Switch 3, do the same thing. Int range of 0, 1 through 24. Shut, short for shutdown. And I'm going to exit. Okay. So we did step 3 on all the switches, we did step 4 just on S1. Now on S2 we need to enable that one interface. So I'm going to say interface F012, switch port mode access. Son of a gun. No shut. change state to up, so that's good. And on S3, we need to bring up interface 18. So interface F018, switch port, mode, AC, tab. Use the tab complete. Switch port mode, access, no shut. Change state to up, so that's good. Now on all the switches, I need to enable interface 1 and 3. Okay, so I'm going to come back to switch 1. Int range F0/1, comma, no spaces. Don't put a space after the comma. We're not typing English, we're typing Cisco. F0/3. That's a way to configure a non-contiguous range. No shut. So what should happen? What's going to happen to my colors when I say no shut? Nothing. Why not? So why would these still be red on S1, even though I just turned them on? Well, it's because these switches, these interfaces are still turned off. Unless both ends are working, we're not going to get our beautiful green blinky lights. So I'm going to exit there. Bring up S2. We're going to run the exact same commands. Int range F0/1, comma, F0/3. No shut. So what should happen now? Anything different? What's going to happen when I hit enter as far as the blinky lights? Think about it. I'll show you in 3, 2, 1. Right, so now S1 and S2, we've got amber lights because these switches, both these interfaces are enabled. They're trying to establish that connection. That's good. So let's come to S3 now. Run the exact same commands. Int range F0/1, comma, F0/3. No shut. Think again, what should happen to my lights? They're all amber or starting to turn green right now, so that is good. So we can run the command do show IP int brief now. I should have 1 and 3 up on all switches and 6 up on S1. I should have, so on S2, if I run do show IP int brief, which interfaces should show up versus administratively down? Think about that. Do show IP int brief. I'm going to expand this so it doesn't wrap funny. So we got 1 and 3 again, but this time we enabled interface 12. So that's good. And on my last computer, sorry, on my last switch, S3, do show IP int brief. We see 18 is up in addition to 1 and 3. Everything looks good. Now we can run do show run here. And we can take a look. We've got our enables, we've got our host name, we've got our interfaces. You can see many of them are shut down. That's their configuration. So if this switch, this configuration was saved and this switch was rebooted, this switch would boot up those interfaces. Turned off, they just simply wouldn't work. We've got interface 6 turned on and it is defined as an access port, so that's good. I'm just going to spacebar to go through all this. I've got my console port configured, got my banner, everything looks good. So I could run that on all 3 switches. It's going to look virtually identical. so I'm not going to run it on all of them. So let's investigate spanning tree now. I'm going to change my options here in Packet Tracer to show the port label. So we've got that we can see that F06 is connected here, F012, F018. Unfortunately, Packet Tracer does not let you position those labels wherever you want to. It does it automatically. Sometimes it does a good job, but when you have a lot of stuff plugged in, it can get kind of confusing. But this will help today. Like right here, if we look at switch 2, we can't see what this interface is, right? We can kind of squeeze it. Okay, it's F01 on the left connecting to switch 1 and F03 connecting to switch 3. Just the way Packet Tracer is. We do the best we can. So we're going to investigate spanning tree. So I'm going to click on switch 1. Now what's going to happen if I say show spanning tree? Hit enter. Invalid input detected. So why did I get this error message? Take a look at these commands that I'm supposed to be running. Why did this fail? If your answer was that that command has to be run in privileged exec mode and not config mode, you are correct. So there are two ways I can fix it to run this command. I could exit and run the command show SPA tab to tab complete, show spanning tree, and that works. Or if I go into back into config mode, I can run do show spanning tree. So just be familiar with both ways to run that command. Both can be useful. I typically prefer running do, so I don't have to exit out and then go back into config mode over and over again. But that's just me. Okay, here we see the interfaces for this switch that have something connected to them. So we have interface 1 connected to switch 2, interface 3 connected to switch 3, and interface 6 connected to computer A. So we have a role and a status. Those are really the columns that we're going to focus here in this table. There can be different roles. Root is the starting point that this network is using to determine kind of the main switch from which all other switches are referenced. If interface is designated, that means it's a preferred path. An alternate would be a secondary path through the network that is not preferred. So on this switch, we have three interfaces. The role is designated, the status is forwarding for all of them. And notice that there are three green blinky lights on that switch. It just means that everything is turned on and it's working as intended. So this is kind of what we expect for switch 1. Let's look at switch 3 first before I go to switch 2. So I'm going to spacebar through that command. Do show spanning. The only problem with running do is that you don't get the tab completion in config mode. You do have to type out the command all the way. That's the only downside. Do show spanning tree. So you'll see this is a little bit different. So F01 is designated, F03 says root, and F018 is designated. The status is it's all FWD, which means forwarding. So this is good, but it's slightly different than we saw on switch 1. Let's take a look at S2 now and compare that. Do show spanning tree. All right. Now we've got root designated, and we've got an alternate. It's interesting to note that this alternate is in a different state. It's BLK, that means it's blocked. Let's look at our diagram. So F03 is blocked. It's an alternate route. And you can see that it's amber. Usually when we don't see green lights, that can be a little bit disconcerting. With spanning tree, we are supposed to see an amber light right here. These switches communicated with each other. Okay, so in the background, they use the spanning tree protocol. We did not have to turn the spanning tree protocol on ourselves. It's just built in. When we connected these switches, we created a potential loop. So if computer A sent out a broadcast message, it would reach switch 1. Switch 1 might broadcast that message. Switch 3 would get it. It could broadcast that out again. Switch 2 would get it, broadcast it out again. Switch 1 would get its own broadcast message and broadcast it out again. That broadcast could continue literally forever. This creates what is known as a broadcast storm. So this loop, we've introduced the potential of having these packets go around forever and ever and ever. So that's not ideal, right? So how could we get rid of that loop? Well, we could disconnect one of these 3 cables, right? If I deleted this connection, computer A could still ping computer B and computer C. The message would just go through switch 3 to get to computer C. To get to computer B, it would go from switch 1 to switch 3, then to switch 2. So all that's fine, right? Well, what spanning tree does, it lets us create a loop, but it will essentially delete this cable for me just by blocking this interface right here. So F03 on switch 2 is blocked, preventing any loops. So all these computers should still be able to communicate with each other. Let's test that though. We haven't made any configurations. Let's go to computer A, desktop tab, IP configuration. This one is going to be 192.168.0.2. Tab fills it in for me automatically. Looks good. I'm going to close it out all the way. Computer B, I'm going to pull up the IP configuration. 192.168.0.3. Subnet masks provided by default is good, so I'm going to close those windows. Computer C, I'm going to change my IP address, 192.168.0.4. Hit tab, the subnet mask again is good. So let's see, computer A, I should be able to ping computer B. So how would I ping computer B? What's my command? Not pointing. Ping 192.168.0.3. I get a reply, so that's good. So for computer A to ping computer B, where's it going? So that ping command is going to switch 1, and then it's going out to switch 2 to computer B. That's our path. I'm going to ping computer C, I'm getting a reply. So it's going from computer A to switch 1 to switch 3 to computer C and back. So that is good. Let's take a look at computer B. Let's try this ping. Where's this ping going to go? Computer B is going to ping computer C. So what's my command? .4. So when I hit enter, okay, get a reply. But this time the path is maybe different than we might expect. Switch 2 and switch 3 are connected directly with a cable, but when I ping computer C from computer B, that ping goes to switch 2 then to switch 1, then to switch 3, then to computer C. It's kind of taking the scenic route. It's taking the long way. It's perfectly fine. It's because this interface 3 has been blocked by the spanning tree protocol. Now, spanning tree, it figures this out all on its own. If we look at the diagram in 6.7, we can see that on switch 1, a different interface was blocked to prevent that loop. It's perfectly fine. The spanning tree just kind of works automatically out of the box, but it kind of figures it out on its own, so it might not always make the same decision for determining which interface to block. But we can have some control over that. We'll see in the next section. So make sure at this point that you know how to discover which interface has been blocked. Now, be able to discover that just by looking at your switch. Look for the amber lights, but also look for that output in the show spanning tree command. Okay, so let's go. We ran show spanning tree. So on switch 2, I'm going to run this command, spanning tree VLAN 1 root primary. And then on S1, ignore that command there. I'm going to change it to secondary. So it's basically going to give switch 2 precedence. So the spanning tree protocol, what's happening behind the scenes is that these switches are communicating with each other. They're sharing link information. And you can see the blocked port just changed. Because S2 became the primary route, essentially its interfaces are given priority, saying we want to use S2 as kind of the backbone of our network. So don't disable any of S2's interfaces if you can avoid it. And we change switch 1 to say, okay, you're kind of the backup, you're the secondary. So now if we run do show spanning tree, on S2 before, one of its interfaces was blocked. None of them are blocked now. Do show spanning tree here. Now we've got, it's defined as root. Everything's up. If we look at S3, Cisco class enable Cisco. I'm not in config mode, so I can just run show spanning tree. I can see that I've got a blocked interface, interface 3. So that's good. The network has converged as soon as these switches have all shared information. So a spanning tree, it takes about 30 seconds. So now we are going to examine convergence. We see here in my network, it was, which one is blocked? F03. Okay, F03 is blocked, F01 is active. I want to find the switch that has the blocked interface, and I am going to turn off the active interface. So on switch 3, I'm going to come configure terminal, and I'm going to configure int F01 because F01 is the active interface. And I'm going to say shut to turn it off. So watch the lights very carefully. Shut. Instantly, these turn red. Watch that amber light though. Kind of be mentally counting in your mind. What just happened, these switches some change happened in the network topology. That's the way it's all wired and configured. Now these switches start to share information to understand this new topology. And when they discover that this loop has been, one path through that network has been disabled, they find a way to fix it essentially. So now you see that F03 just turned green. That's because of the spanning tree protocol. It automatically enabled that interface for us. So that's fantastic. We added a little bit of redundancy to our network, and it was able to heal itself essentially from a network failure. So everybody should still be able to ping each other. Computer B should still be able to ping computer C, just through a different path than maybe what happened would have happened previously. So that is good. So be able to trace the path, verify that your computers can still connect. So in all of my switches, I'm going to run the command spanning tree mode rapid pvst. See, it's making some changes there. Spanning tree mode rapid pvst. Okay, so run that command. You probably saw some changes in the blinky lights temporarily. It's all fine. But now it looks the same as it was 2 minutes ago after I disabled F01 on switch 3. Now I'm going to come back to S3 and I'm going to configure F01. Now I'm going to turn this interface back on. How do I do that? We did this at the beginning. I'm going to say no shut. So think about what's going to happen. The light should turn amber briefly. The switches will communicate to figure out the topology and figure out what interfaces to turn off. So see how long this takes now. I'm going to hit enter. Amber lights, thinking, okay, another port, a different port was turned off this time. And how long did that take? Maybe 1 to 2 seconds. Previously, with the regular spanning tree protocol, it took about 30 seconds for the network to converge. I'm going to shut down F01 again, just with the shut command. And let's count. 1001, 1002, 3. Oh, it happened so fast. I was counting how long after that interface was turned on. Let's do this. No shut. Bam. It's almost instantaneous. It's much, much faster. So that's a good thing. Now, a good thing about rapid PBST Plus is that your network converges much, much faster. So if a cable got cut, so I'm going to turn this back on. Let's say that this cable is physically removed from my network. My users aren't going to notice much, if any, interruption at all. So that's a good thing. One downside with rapid PBST Plus, and maybe the only downside, is that it's proprietary. That means Cisco owns it, and unless you're working with a bunch of Cisco gear that all supports it, you can't run it. So if I had a Hewlett-Packard switch, and a Cisco switch, and a 3Com switch, and I connected them all together, I wouldn't be able to use rapid PBST Plus. I would have to stick with the regular spanning tree protocol, which is open and available to everybody to implement. So let's look at the learning checkpoint. You should be able to describe the purpose of the spanning tree protocol. You should be able to identify potential loops in the local area network, determine which interface is blocked by spanning tree, change the primary and secondary root bridge, and you should be able to describe the benefits of Rapid PBST+, and you should be able to enable Rapid PBST+. There should be no question mark there. That's just a typo. I apologize. So for the submission, I would just want you to run show spanning tree, do show spanning tree, show me its output. When you're done, just reset all the configurations and everything will be good to go. Put all the cables away nicely, please. And next time we'll talk about subnetting basics. Thanks, everyone.